Hi, my name is Sunnie Kim, and today I will present our work, Deformable Style Transfer. This work was done with Nick Kolkin, Jason Salavon, and Greg Shakhnarovich while I was a visiting student at TTIC. Style transfer is a popular task in computer vision and graphics, where the goal is to re-render the content of one image using the style of another. The performance of recent methods have been exciting and have certainly captured the public's attention. However, most methods only consider color and texture and ignore shape and geometry, which are also integral parts of visual style. So we asked the question, can we also transfer shape and geometry? It turns out the answer is yes, as shown in these two recent works, but only on human faces so far. Both methods learn to mimic spatial style. The face of art learns an explicit model of facial landmarks, and WarpGAN learns a deformation model that represents a specific style. Their performance is impressive, but they require a collection of images in the chosen style and only work in the specific domain of human faces. On the other hand, we're interested in a more general scenario where we can do one-shot geometry-aware style transfer for non-face images. To go beyond color and texture transfer, we propose deformable style transfer, abbreviated as DST. Our method takes two images as input, a content image and a style image, which we assume to share a domain and have similar geometry. This is a general scenario likely to arise in recreational or artistic uses of style transfer, as well as in tasks such as data augmentation. The key idea of DST is to find matching key points between the images and use them to deform the output image to bring it into spatial alignment with the style image. We find correspondences using neural best buddies, a generic method for point matching between images. The correspondences returned by neural best buddies, however, are often sparse, noisy, or not sufficiently spread out to use them as they are. So we modified the method to get a cleaner and better spatially distributed set of points. Next, we map the key points in the style image onto the content image by finding a similarity transformation that minimizes the squared distance between the two point clusters. We refer to the key points in the content image as the source points, and the corresponding transformed key points from the style image as the target points. Finally, an image can be spatially deformed by moving a set of source points to a set of target points. Naively warping the image in this way, however, can create a drastic deformation with undesirable visual artifacts. So in deformable style transfer, we optimize the actual deformation parameters jointly with other stylization parameters. Our method can be used with any one-shot optimization-based style transfer method with a content loss and a style loss. In this work, we demonstrate DST with two such methods, Gaddis et al. And Strauss. The input to DST is a content image, a style image, a set of source points, and a set of target points. We jointly optimize the stylization parameters X, which are usually the pixels of the output image, and the deformation parameters theta that determine where the source points move to. The final output is the warped stylized image, W of X and theta. Now I'll go over the loss terms one by one. First, L content is the content loss as defined by the base method. Usually, it's some measure of difference between features of the content image and features of the output image. L style is the style loss, also as defined by the base method. Here, in addition to the usual style loss, we also calculate the same loss between the style image and the warped output image. This helps in finding a good stylization both with and without deformation. Then we have our deformation loss L warp, that is the mean L2 distance between the optimized destination points and the target points. This term encourages the geometric shape of the output to become closer to that of the style. However, aggressively minimizing this loss may lead to significant visual artifacts, so we regularize the deformation with the total variation norm of the 2D warp field that encourages nearby pixels to move in a similar direction. Lastly, Alpha and beta are hyperparameters that control the relative importance of content preservation and deformation to stylization. And gamma controls the amount of regularization on the deformation. We use standard iterative optimization techniques such as stochastic gradient descent to minimize this objective with respect to x and theta. Here we show the input content and style images, the output of the base style transfer method STROTs, and the DST output. To highlight the effect of the deformation, we also provide the STROTs output naively warped with the selected key points without any optimization of the deformation. We also show the content image warped with the deformation parameter optimized by DST. In this example, we can see that the bag the woman is carrying has been made flatter in the DST output to better match the shape of the style image. In this another example, we can see that Ezra Miller's face has elongated in the DST output to better match the geometric style of the caricature. Again, DST produces a much smoother and a more aesthetically pleasing image compared to the naive warp. Here we show more examples. Each set of 3 contains a content input, a style input, and our method's output. We observe that DST captures the geometric style of the target style image in addition to color and texture. Even in the constrained face domain, where existing methods use tailored mechanisms, our results are competitive and sometimes more aesthetically pleasing than results from these methods. DST also flexibly supports matching points found by methods other than neural best buddies. Here we show 2 examples, one with points discovered by Face of Art's facial landmark detector, and another with points manually selected by a user. We see that cleaner key points give better results, both in our method's output and in the naive warp, suggesting that as key point detection methods improve, so will DST results. To quantitatively evaluate DST, we conducted a human evaluation study using Amazon Mechanical Turk on a set of 75 diverse style and content pairs. The goal was to study the effect of DST on the stylization and content preservation trade-off. To measure content preservation, we asked the mTurk users, does image A represent the same scene as image B, where A referred to the content image and B to an output of style transfer? To measure stylization, we presented the users with a pair of outputs, one from the base method and the other from DST, along with the style image. Then we asked which of the 2 output images better matches the style. Specifically, we compared the output of the base method Gaddis or STROTs and 3 DST outputs, each with a different level of deformation. We have 4 content comparisons, one for each style transfer output, and 3 style comparisons, one for each DST output against the base method's output. Here are the results. Higher content scores towards the right indicate better content preservation, and higher style scores towards the top indicate better stylization. Across the 3 deformation regimes for both STROTs and Gaddis, DST significantly increases the perceived stylization quality while only minimally reducing the perceived content preservation. Note that some hit to the content score can be expected since we, in a sense, willfully alter the content by deforming it. In summary, so far as we're aware, we demonstrate for the first time geometry-aware style transfer in a one-shot setting. We do this with automatic deformation of images integrated into an optimization-based method. And in contrast to previous works that are limited to human portraits, our methods works for images in other domains with the assumption that they share a domain and have some approximate alignment. We also allow explicit user guidance and control of stylization trade-offs. If you want to learn more about our work, please visit the following links.